So I wanted to talk about fields, and I'm going to use the electrostatic equation to talk primarily about fields instead of the gravitational. Gravitational is a one-directional field. It's always pointing inward. So I wanted to look at electrostatic fields instead because we have that dynamic between positive and negative, and those fields can both go inwards and outwards depending on the charge. Okay, so what I'm going to do is I'm going to create myself a little proton. Woohoo! There's my little proton. Okay, positive charge in the universe. Make it a little darker. I need some bigger chalk. Okay, so it's a positive charge in the universe. Now looking at this equation, let me write it closer to the proton. Okay, KQQ over R squared. Now, if I introduce another proton into the field, I can determine the direction of the force. Now, I've already used the word field, and I guess I shouldn't. Let's say I introduced another proton, and leaving the field out. We can already determine the direction of that force, right? KQQ over R squared. There's no negative sign like gravitational. Okay, so the force that this one right here, we'll call it 1, does on this one, which we call 2, we can determine the radius. So radius starts from the center and moves out. Okay, there's R right there. So the direction of the force is in the direction of R. That's why we have this R hat notation. So this charge is being moved, or is being pushed at least, not necessarily moved, in that direction from that charge. And then vice versa. If we talked about this one to this one, then the radius starts from here and moves to this direction, so the force is going to be that way. Okay? So we have to have two charges in this system to create a force. Okay? So it's not always to our advantage to talk about this as forces. Instead, we come up with another language. We come up with the word fields. Okay? So when we talk about an electrostatic field or a gravitational field, which everybody's heard, or even a magnetic field, we're talking about this region of space that could create a force if a charge was being introduced into the system. So this charge will create a field without another charge. It won't create a force without that other charge. It will create a field though. Okay? Cool? So that's the idea of fields, is to get this idea of a potential of a force. There's a force waiting to happen. As soon as I drop something into that field, a force is created. Or vice versa, it requires a force to take that object and to put it in that field. So if you can determine what that system is, you've got a back door there too. So anyway, KQQ over R squared is our force, but I don't want to talk about forces. I want to talk about fields. I want to talk about electrostatic fields. Okay? And I'm going to use the notation E for electrostatic fields. Now, one thing I should be careful about, because we can think of E as being energy, we should remember that these are vectors, and I should be using vector notation on them. Okay, so a field by one charge. Well, what do I have to do to this equation to come up with another equation that only contains one charge? Divide by a charge. Divide by charge 2. If I want to figure out the field that's being created by 1, I need to divide charge 2 out of my equation. So if I divide by that charge, what am I left with? I'm left with KQ R squared R hat. That's my equation for a field. K, the permeability constant of the universe for electrostatic fields. Q, a coulomb, the charge 1 here. R squared, the radius, well, we don't really have a radius, but we'll talk about that in a second. R hat to give me my direction, and then is equal to my electrostatic field. Okay, so what I've done is I've divided this charge out. It is now gone. Okay, and I'm only left with this single charge. Now I want to determine what the field is in this situation. Well, the field is, well, I got my one charge. That field is, well, at this point, it's equal to KQQ over r squared, whatever that r squared may be. So I may have a field that looks like this at that point. Okay, remember this length is determining the magnitude, the tip of the arrow is determining the direction. Okay? But it's r, it's radial, which means that anywhere in that radius I'm going to get the exact same length on that arrow. Okay? They're all going to be the exact same size if I stay at that radius. Cool? That's for a single charge creating that field. Now, the reason why we would do this, the reason why we would end up creating electric fields, is that electric fields are much in the same way like forces. They have a superposition associated with them. And superposition is just a fancy way of saying that they have additive properties. Okay, so if I had introduced another charge over here, okay, another positive charge, excuse me, this positive charge is going to create a field like this. Okay, remember magnitude, direction. So the advantages of this system is now that I can talk about these two objects, and if I introduced a third object, I can find a point where I can put that third object and it can be in equilibrium. What kind of situation would I have two objects, each of them generating a field and a force, and I want to take an object and I want to put it in equilibrium so that it doesn't fall towards either one of those objects? Well, it's simple. Satellites. Satellite motion. You can put yourself into a nice field here where you're experiencing no gravitational attraction. You get a stable orbit. There's other ways to get stable orbits, mind you. If you talk about brain slipping. Uniform circular motion. If you're going fast enough, you're going fast enough. You're moving far enough in one direction to overcome the distance that you're falling. So you're achieving this uniform circular motion. But you also can achieve this little stationary orbit here, where this object can just sit here in this region between these two objects. Okay, so fields are a great way because you can say, look, this arrow plus this arrow is going to give me this arrow, or 0 arrows, or this arrow plus this arrow means that these components may cancel out each other, but the components in this direction are now getting bigger. Wow, that's interesting. So that means if I put a charge here, an object here, in this case a charge, it's kind of stable. Well, hold on, look at it. Go down here. Look, I've got a force. I got my field in this direction. I drop a positive charge in here, it's going to stay. But if I nudge it, or if I'm a little off, it's going to go boom in this direction, or boom in this direction. Okay? So that's the real advantages of talking about fields, is that you've got an idea where these stability points are. You also have an idea where these objects are going to experience the greatest amount of forces. And then lastly, when you're dealing with a tremendously high number of objects, aka capacitors, or, I mean, you don't really normally do it for gravitational fields, but electrostatics most certainly, capacitors, wires, all sorts of stuff, that fields are a nice way of summing up all those forces together to get a net electric field from all these objects without having to talk about forces, because you don't necessarily have to have a charge there. You just have a field. Okay? I hope that makes sense. That's an electrostatic field. It's a field in general that this object is pushing out. Okay? Well, it's positive charge, so it's pushing out. And they're additive. They can add via superposition. This much this way, this much this way, this much this way, this much this way. These kind of cancel each other out, but these are additive. They increase the field strength in that direction. As a matter of fact, you would end up getting something like this as your field diagrams. Okay? They would tend to be, curving in this direction. So that also means if I drop the charge here, it would tend to curve along those field lines. Cool? Now what I'm going to do next is I'm going to introduce an electron and see how that affects my field.